53 years. That is how long we told ourselves we understood the moon. 6 landings, hundreds of kilograms of rock samples, decades of orbital imagery so detailed you can count individual boulders from Earth. We built textbooks around it. We taught it to children. We called it settled. Then on April 6, 2026, 4 astronauts swung around the lunar far side aboard Orion. And within hours, everything we thought we knew started to crack. Not because they found something impossible, because they found something that our best models cannot explain. A landscape so fundamentally different from the side we have stared at for millennia that calling them the same object feels like a category error. A buried mass so dense it warps the local gravity field. A thermal signature that should not physically exist. Geological features that require conditions the moon was never supposed to have. Victor Glover, a Navy captain and test pilot with 168 days aboard the International Space Station, tried to describe what he was seeing in real time. He said humans have probably not evolved to see what they were looking at. Think about that. A man trained to stay calm when engines fail at altitude. A man who has floated in orbit for months and the moon made him run out of words. If the data coming back from Artemis II holds up under scrutiny, we are not looking at a minor revision to lunar science. We are looking at a rewrite. Subscribe so you do not miss what comes next. Now, let us go through exactly what they found and why it should unsettle you. To understand why what Artemis II recorded is so significant, you first need to understand something that most people never think about. The moon you see every night, that familiar grey disk hanging in the sky, is not the whole moon. It is half of one, and the half you cannot see is a completely different world. The side facing Earth, the near side, is covered in vast dark plains called Maria. Ancient lava flows that poured into enormous impact basins billions of years ago, cooled and solidified into flat basalt seas. Roughly 31% of the near side is blanketed in this smooth volcanic rock. It gives the moon its recognizable face and the one we have painted, photographed, and navigated by for thousands of years. The far side has almost none of it, less than 1%. Instead of smooth plains, the far side is a wall of craters, stacked on top of craters, stacked on top of older craters, ancient, battered, and relentless, as if something took a hammer to it for 4 billion years and never stopped. But the visual difference is only the beginning. The crust on the far side is roughly 50 kilometers thicker than on the near side. The chemical composition is different. The thermal history is different. The distribution of radioactive elements is different. These are not subtle variations. These are the kinds of differences you would expect between two entirely separate planetary bodies, not two faces of the same object. Here is the analogy that matters. We build our entire model of the moon based on data from one side. That is like landing a spacecraft in the Sahara Desert, collecting sand samples from a 2-kilometer radius, and then publishing a comprehensive geological atlas of the entire Earth. We were not wrong to work with what we had, but we were overconfident about what it told us. That overconfidence is exactly what Artemis II just started to dismantle. The crew of Artemis II launched from Kennedy Space Center at 6:35 in the evening on April 1st, 2026. 4 people, 1 spacecraft. The most powerful rocket NASA has ever built. Their names are Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen. Wiseman commands the mission. Glover is the pilot. Koch and Hansen are mission specialists. Between them, they carry a weight that goes beyond the technical. Glover is the first black astronaut to travel beyond Earth orbit. Koch is the first woman. Hansen is the first non-American. 53 years after the last Apollo astronaut left the lunar surface, humanity finally sent a crew that looks more like humanity. The space launch system that carried them stands 322 feet tall and generates 8.8 million pounds of thrust at liftoff. It pulled them out of Earth orbit in a single engine burn lasting less than 5 minutes. From that moment, turning back was no longer a simple option. The trajectory they followed is called a free return path. It means that even if the spacecraft's engine had failed completely after that initial burn, the moon's gravity would have captured them, swung them around, and sent them falling back toward Earth on its own. Apollo 13 survived because of this same principle. The fact that this is considered the safe option tells you something important about the nature of the mission. At their farthest point, the crew reached an estimated 252,756 miles from Earth, the farthest any human being has ever traveled from this planet. And then came the 40 minutes that no training can fully prepare you for. As Orion passed behind the moon, every radio signal between the crew and Earth was cut off completely. No voice from Houston, no telemetry, no abort commands. 4 people sealed inside a capsule roughly the size the size of a large van, alone with the oldest and most battered landscape in the solar system stretching out beneath their windows. Let us start with the largest wound in the solar system. The South Pole Aitken Basin sits on the lunar far side, straddling the southern hemisphere. It stretches roughly 2,500 kilometres across and plunges up to 13 kilometres deep. If you placed it over a map of the United States, it would swallow everything from Texas to Virginia. The mountains along its rim reach summit elevations of 8,500 metres, taller than any peak in the Alps. It is the largest preserved impact crater we have found anywhere in the solar system. And the Artemis II crew became the first humans to see its eastern edge with their own eyes, not through a robotic camera, not in processed data from an orbiter, through the windows of their spacecraft at an angle and under solar illumination that the Apollo flight paths never allowed. That alone would be historically significant. But what is buried beneath that basin is what keeps planetary scientists up at night. In 2019, a team led by planetary geophysicist Peter James at Baylor University combined gravity data from NASA's Grail mission with topographic measurements from the Lunar Reconnaissance Orbiter. What they found was a mass anomaly sitting at least 300 kilometres below the surface of the basin, a concentration of extraordinarily dense material with a minimum estimated mass of 2.18 quintillion kilograms. To put that in terms, you can feel, James described it as roughly equivalent to burying a pile of metal 5 times larger than the big island of Hawaii, somewhere deep underground. Whatever it is heavy enough to drag the basin floor downward by more than half a mile. You can measure its gravitational pull from orbit. Now, mass anomaly is the technical term. What it means in plain language is this: something is down there that does not match the surrounding rock, and it is pulling on everything above it. The leading scientific hypothesis, and it is important to be precise here, this is a hypothesis supported by gravitational data, not a confirmed fact, is that this anomaly represents the metallic core of the asteroid that created the basin in the first place. An impact is so massive that when it struck, its iron-rich core did not vaporize completely. Instead, it sank into the lunar mantle and stayed there. 4 billion years later, it may still be lodged in place. Like a bullet fragment the body never managed to push out. If this hypothesis is correct, the implications extend beyond geology. An impact large enough to leave that kind of remnant would have released energy sufficient to send shockwaves through the entire lunar interior. Some researchers propose it may have been violent enough to shift the moon's rotational axis, to physically reorient the whole body in space. The Artemis II flyby did not resolve these questions, but it gave scientists something they did not have before, direct human observation of the terrain above this anomaly at angles and resolutions that orbital imagery alone cannot capture. Every photograph the crew took of that region is now a data point in an investigation that has been running since 2019 and still has no definitive answer. Now, here is where the far side stops being merely unusual and starts being genuinely difficult to explain. In 2023, a research team analysing thermal data from the Lunar Reconnaissance Orbiter detected something buried beneath the far side surface that had no business being there. A region approximately 50 kilometres wide, registering roughly 10 degrees Celsius warmer than everything around it, not on the surface. Beneath it, a heat source, quiet and persistent, radiating upward through kilometres of lunar rock. The most probable explanation, according to lead scientist Matt Siegler and his team, is a massive buried block of granite, and that is where the problem begins. Granite is one of the most common rocks on Earth. It forms the cores of continents. It builds mountain ranges. You have almost certainly touched it. Kitchen countertops, museum floors, city monuments. On Earth, granite is unremarkable. On the moon, granite is essentially forbidden. Here is why. Granite forms through a specific geological process called silicic volcanism. It requires 2 things that the moon is not supposed to have: liquid water and plate tectonics. Water lowers the melting point of silicate rock and allows the chemical separation that produces granite's distinctive mineral composition. Plate tectonics provides the pressure and recycling mechanisms that drive the process over millions of years. The moon has neither. It lost whatever water it had in its earliest history. It has no tectonic plates. By the standard model of lunar geology, a buried granite formation of this scale simply should not exist. And yet the thermal signature is there. Measurable, reproducible, sitting underneath the far side like a question the moon has been waiting 4 billion years for someone to ask. Siegler's team proposed that this formation may be the remnant of an ancient volcanic system that went dormant approximately 3.5 billion years ago. Its residual magma slowly cooling, but still warm enough even now to register as a thermal anomaly from orbit. Think about that timeline carefully. 3.5 billion years of cooling, and it is still warm. To be precise about the boundaries of what we know, this thermal anomaly is a confirmed observational fact. The granite hypothesis is the leading scientific interpretation of that data. What formed it and whether the moon had conditions we currently cannot account for remains an open question, one that no existing model answers cleanly. The far side is not just geologically different from what we expected. It is different in ways that challenge the foundational assumptions of how we think moons form and evolve. So we have two sides of the same object that look chemically and structurally like they belong to different worlds. The question science has been wrestling with is straightforward to ask and remarkably difficult to answer. How did this happen? The dominant theory of lunar formation holds that roughly 4.5 billion years ago, a Mars-sized body collided with the early Earth. The debris from that collision, a molten rock, vaporized material, fragmented crust, coalesced in orbit and gradually solidified into the moon. This is called the giant impact hypothesis, and it is supported by strong evidence from isotopic analysis of lunar samples. But here is the problem. The giant impact hypothesis, in its standard form, does not predict the asymmetry we observe. It does not explain why one hemisphere ended up covered in ancient lava plains while the other became a cratered wasteland. It does not account for the crustal thickness difference of 50 kilometers, and it certainly does not explain granite that should not exist. The South Pole Aitken mega impact theory attempts to fill part of this gap. The hypothesis proposes that an enormous secondary impact near the lunar South Pole sent a pulse of heat rippling through the entire lunar interior, driving radioactive elements and rare earth materials toward the near side. This would explain some of the chemical asymmetry we observe, but seismic data collected by NASA's InSight lander reveals internal temperature gradients that do not perfectly align with what this model predicts. The pieces fit together partially, not completely. To be fair to the scientific consensus, and fairness here matters, many researchers maintain that the asymmetry can be explained within existing frameworks given sufficient modeling complexity. That position is not unreasonable. But the granite formation and the mass anomaly beneath the South Pole Aitken Basin remain stubbornly outside those frameworks, two data points that sit at the edge of what current theory can accommodate. The universe does not care how elegant our equations are. It runs on its own logic. And right now, the far side of the moon is running on logic we have not fully decoded yet. Pull back from the geology for a moment, because there is another layer to what Artemis II represents, one that is not about rocks or gravity anomalies, but about the raw physical vulnerability of being human in deep space. The mission launched during solar maximum. That is the peak of the sun's 11-year activity cycle, the period when solar particle events, sudden eruptions of high-energy radiation from the solar surface, are most frequent and most intense. A severe solar storm can push radiation exposure toward nearly lethal doses within hours. The Orion capsule provides more shielding than Apollo ever did. But galactic cosmic rays produced by supernova explosions and other cataclysmic events across the universe travel at nearly the speed of light and penetrate almost anything we can reasonably build and launch. Right now, as you are watching this, those same particles are passing through your body. Every second, what protects you is something you cannot see and rarely think about: Earth's magnetic field, a planetary scale shield generated by the churning iron core beneath your feet. Step outside that shield, as the Artemis II crew did, and the exposure increases dramatically. Only 24 human beings have ever left Earth's magnetic protection. 24? That is not a sample size from which you can draw statistically meaningful conclusions about long-term health effects. We are essentially operating in the dark. The Avatar payload aboard Artemis II carries bone marrow cells derived directly from the crew's own blood. Scientists will study how those cells respond to the deep space radiation environment after splashdown. That data may be worth more than every photograph the crew took combined, because photographs tell us about the moon. Those cell samples tell us whether humans can survive long enough to do anything meaningful once they get there. And during those 40 minutes of complete communications blackout, none of that mattered in any practical sense. If a solar particle event had struck at that moment, mission control would not have known until the signal returned. 4 people, no contact, no rescue possible. Surrounded by ancient violence, bathed in radiation, our species did not evolve to survive. That is not a malfunction. That is the mission operating exactly as designed. Here is the dimension of the far side that almost nobody talks about, and it may ultimately matter more than anything the geology can tell us. The far side of the moon is the quietest place in the inner solar system. Every radio signal generated by human civilization, every cell tower, every broadcast antenna, every satellite transmission, every router in every building on Earth is blocked by 3,400 kilometers of solid lunar rock. Permanently, the far side does not just muffle that noise, it eliminates it completely. For radio astronomers, this is not a convenience. It is a scientific instrument unlike anything else available to us. Telescopes placed on the far side could observe frequencies below 30 megahertz, a range that Earth's own ionosphere blocks entirely, making it invisible from any ground-based or Earth-orbiting observatory. That frequency range corresponds to signals from the cosmic dark ages, the period before the first stars ignited when the universe was nothing but cooling hydrogen gas and silence, a window into the earliest moments of cosmic structure that we have never been able to open. Think of it this way. You are trying to hear a whisper from 13 billion years ago, but you are standing inside a stadium during a rock concert. The far side of the moon is the only soundproof room we have access to. China understood this early. Chang'e 4 landed on the far side in January 2019. Chang'e 6 returned physical samples in 2024, the first material from the lunar far side ever analysed in an Earth laboratory. The race for the far side is not about flags. It is about who gets to build the observatory that hears the universe most clearly. So where does this leave us in April 2026 right now? The Artemis II crew splashed down on April 10th off the coast of San Diego. The thousands of photographs taken during the flyby are still being downlinked and processed. The full image dataset will take months to analyse completely. Scientists are already working through the Chang'e 6 far side samples collected in 2024, and preliminary findings are expected to reshape at least some aspects of current lunar formation models. Artemis III, currently targeting 2027, will attempt the first crewed landing on the lunar surface since December 1972. The planned landing zone sits near the South Pole, on the rim of the South Pole Aitken Basin. The first boots on the ground will touch down directly above the largest and least understood structure on the moon. The lava tubes remain sealed. No approved mission currently exists to enter them directly. What they contain, trapped gases, pristine volcanic deposits, temperature environments radically different from the surface, remains entirely speculative. The mass anomaly 300 kilometers beneath the basin floor has no confirmed explanation. The granite formation has no agreed origin. The thermal anomaly is still radiating heat from something 3.5 billion years old. These are not gaps at the edges of our knowledge. They are gaps at the center of it. The question worth sitting with is this: if 50 kilometers of additional crust and a buried mass the size of 5 Hawaiian islands went unexamined for this long, what else are we confidently wrong about? We have stared at the moon every night for the entire history of our species. We drew it, worshipped it, navigated by it, wrote poetry about it. We landed on it 6 times and came home convinced we understood it. But every landing was on the near side. Every sample came from the near side. Every conclusion we drew about lunar geology, lunar history, lunar formation built on data from one hemisphere, half the object. And we called it knowledge. That is not a criticism of the scientists who came before. They worked brilliantly with what they had, but there is a difference between knowledge and the appearance of knowledge. And for 53 years, we were living inside that difference without fully realizing it. You are watching this in April 2026. 4 days ago, for the first time since 1972, human eyes looked at the far side of the moon from close range. Not a robot, not a sensor array. People, and what they saw made one of the most composed and experienced astronauts NASA has ever produced say that human beings have probably not evolved to process what he was looking at. The moon is not a poster in the sky. It is a place, a real complicated, unresolved place that has been holding its secrets at a distance of 250,000 miles this entire time, and we have barely begun to ask it the right questions. What do you think Artemis III will find when it actually lands on that surface in 2027? Leave your answer below, because at this point, the honest answer is none of us truly know.